Video will be about galvanic cells. So the purpose of galvanic cells is to convert stored chemical energy into usable electrical energy. And it does this by the redox reactions and the transfer of electrons. The structure of a galvanic cell consists of two electrodes. In this case, it's the zinc electrode and the copper electrode. And these electrodes are blocks of metal dipped into their own metal solution, in this case zinc nitrate and copper nitrate. And it's important that these metals are dipped into the same solution of the metal, zinc with zinc and copper with copper. So these are your two electrodes. There are two types of electrodes. There's the anode and the cathode. The anode is the electrode where oxidation occurs, and the cathode is where reduction occurs. An acronym for that is anox red cat. Oxidation is the loss of electrons, while reduction is the gain of electrons. Another acronym for that is oil rig, where the oxidation is loss of electrons, reduction is gain of electrons. So with these two electrodes, these are also your electrolytes, the solution where the electrodes are dipped in, and this is your salt bridge to create neutrality of the charges of electrons. This is your voltmeter, which is to determine the cell potential of a galvanic cell occurring. So basically, how a galvanic cell works to create electrical energy is that in our redox reactions, our metal wants to be in a solution as it's more reactive. For example, if we look at our formula sheet, the standard potentials show zinc being on top of copper, meaning zinc is more reactive than copper. And we know that the more reactive metal wants to be in a solution. And because zinc is more reactive than copper, we know that zinc wants to be in its solution. So these are zinc atoms. We know because it wants to be in a solution, it must undergo oxidation. When oxidation occurs, it loses two electrons. When it loses two electrons, these zinc atoms fall into the solution to become Zn2+, while the two electrons travel all across to the other cathode. and the electrons fall all the way into the solution, where they combine with the solution to form copper atoms within the cathode. And we could see, because this solution is split into copper 2 ions and nitrate ions, where these two electrons form with this ion to create a copper deposit on the cathode. And as that occurs, these zinc electrons are unstable, and this is why we have the salt bridge. As zinc ions accumulate, and because the copper ion is collected by the electron to create a deposit, which leaves us with nitrates, these salt bridges achieve neutrality by splitting into A plus and NO3 minus. These nitrates from the salt bridge go down to form with zinc 2 plus to form solution, whilst the anode decays. At the same time, potassium ions travel down to the solution and combine with nitrates, which creates potassium nitrate solution. And over time, the charges of electrons moving over from the anode to the cathode, where zinc falls down into solution, will eventually stop until all of the anode decays and the cathode gains a bunch of copper atoms. So that's pretty much how galvanic cells work, where the voltmeter measures the cell potential of the electron transferring. Another thing you need to know is that the salt bridges aren't always potassium nitrate. Most of the cases it is, because all nitrates are insoluble, which means they do not dissolve in any solution here. Now let's move to a practice paper. Question 24 of North Sydney Girls paper. Complete the diagram below to show the galvanic cells described above. In your diagram, clearly label the anode, cathode, salt bridge solution, and all the other stuff. So, firstly, we're given the two metals to be copper and tin. First, we look at our formula sheet and look at the standard potentials. We could see that tin is more reactive than copper. Which means tin wants to be in solution. And if it wants to be in solution, it must undergo oxidation. So let's write our electrodes. We'll also add the voltmeter and the salt bridge. It says to use a potassium nitrate salt bridge. So we labeled our anode and cathode and the salt bridge. Now we gotta do the solution. Looking at our standard potentials, SN tin undergoes oxidation to lose 2 electrons. If our salt bridge is nitrate and tin loses 2 electrons, which means it has a positive charge of 2, then the solution would be we know copper has a charge of 2 plus, which means there'll also be 2 nitrates with it. So now we've labeled our solutions. Now we gotta label our direction of electron flow. We know Sn is more reactive than copper, so it will want to go into the solution, right? In order to go into the solution, it must lose electrons, which means that electrons travel this way. And now we gotta write the direction of ion flow across the salt bridge. So because Sn loses electrons, it forms Sn2 plus ions in the solution because the atoms fall down into the solution. And to create neutrality, the potassium cation, wait no, the nitrate anion must join up with tin to create a solution. That's why NO3 goes down this way. And because these electrons move over into the solution to create more copper atoms, it leaves us with a lot of nitrates. And to combat this negative nitrate, the potassium must go down to form a potassium nitrate solution. And that's the diagram. Write the oxidation and reduction half equations. So we know tin is the anode, And using the acronym Anox Red Cat, the anode undergoes oxidation, so no tin undergoes oxidation. We know oxidation is the loss of electrons, so we can write Sn loses 2 electrons, and reduction. We know reduction occurs at the cathode. This is our cathode. And reduction is the gain of electrons. So Cu2 plus in the aqueous solution plus 2 electrons creates our copper solid cathode. Now calculate the theoretical electrical cell potential of the galvanic cell. Looking at the formula sheet, we know Sn2 plus 2E minus, that gives us tin solid, is negative 0.14 volts. However, all of these equations in the standard potentials are all reduction equations. Thus, in order to convert these reduction equations to oxidation values, we must switch the minus 0.14 volts in the tin potential by negative 1. And the opposite of minus 0.14 is positive 0.14. So that's for tin. Now we find copper. Copper is already in the formula sheet. The equation for copper is already in a reduction. So it already says 0.34. And now I just add these values together, which would give us 0.48 volts. And that's galvanic cells.